Good morning, everyone. Today is June 27th, no, 20th, June 20th, 2020, and this is the John Chappell Natural Philosophy Society Science Chat. I am your host, Franklin Hu, today. And with us today, we have Dennis. Dennis is here, and James is here. So welcome, guys. So I was thinking we would talk about the magnetic field today, since that seems to be quite the hot topic in the email. There's been this huge thread that I have not been able to keep track of about how an electron in a conductor is affected by a magnetic field. So that sounds like a good topic to discuss. We also have Bill Lucas watching us today on YouTube. So once again, anyone who's watching this on YouTube, please feel free to give us a chat if you have a question. And let's see here. So James just stepped out there for a second, but it sounds like he's got a brief update of work on alpha, whatever that means. So there you are, James. So you say James, you have an update on alpha?
Right. I just put out a very short paper last night on the work on alpha that I presented here. I think it was about 2 weeks ago. And this work corrects some minor errors in what I said two weeks ago. There's also an update of the Binary Mechanics Lab simulator and version 2.8, which contains the correction with respect to the calculation of alpha. And so if there's time, I can present that information, today or when possible.
Let's see. Just remind me. So, what is alpha? That constant is
the structure constant.
Yes, defined structure constant.
Yeah, which has been much discussed for many decades in physics. The quantum electrodynamic guy, Richard Feynman, well-known physicist, said that every physicist should have this value of alpha up on their wall as one of the great mysteries of physics to be solved. So maybe we're on the track of solving it. I don't know.
So materially, did you change your? Was it just a correction, or did you have some?
Well, yeah. The calculation done previously was based upon the values displayed in the simulator at the end of each tick, and the critical value as to the charged quanta or quanta with a charge attribute was the m value, which is the denominator in the equation. But that is slightly wrong. It should have been the m value at the beginning of the tick before the time development laws were applied, because those are the quanta which could be acted upon or are accelerated by an electromagnetic or an electrostatic or a magnetic potential in the time development laws used to generate the new system state display in a particular BMLS tick. So that was a slight programming correction, and I realized that. I said, yeah, I got the right variable, but not exactly at the right time, and it makes a little bit of difference. You want things to be accurate. So I could go into a little bit more detail. Plus, if there's time, I'll share my screen and show you what I have.
Well, I suppose You could do it now, I suppose. This will be the
Okay,
topic if you want to do that.
let's see if I get the
But
screen shared here. Share
although
screen.
I think it's pretty clear that you
And then
can't.
I click here. I don't know why you have to click so many times.
Yeah, you have to click a lot of times.
I'm
So did
clicking
that
share
make
screen again, and then share.
and let's see here. I should be picking up your
Oh,
screen.
I have to click on the image and then share. And then here is the paper published last night. Very briefly, since I discussed this 2 weeks ago, I'll sort of skip over a lot of the text here. But just to refresh people's memory, some consequences of defining the fine structure constant alpha as the probability of an electromagnetic interaction with a charged particle are explored using the simulator. An alpha composite variable was introduced. See, here is the the number of m quanta, which I designate now as m sub zero, meaning at sort of time equals zero for a current tick. Then the scalar and vector operations are applied. And how many scalar or vector operation events occur? An event meaning that all the criteria are met so that the mite or m-type particle or quanta is accelerated. That is our proportion. Okay. So skipping on down quickly, I won't read all this because it's in the paper that you can look at. It's the most recent publication. The alpha variable was not constant, but varied as a function of quanta density in the simulated volume. Now, if you go back to the Wikipedia page on the fine structure constant alpha, you find there is a lot of discussion concerning alpha possibly being energy density dependent. In fact, the whole area that the particle physicists called gauge, what do they call it? Gauge theory, that the coupling constants of all of the forces that they imagine actually can converge at a certain point to get some kind of a grand unification. That concept of the constant or coupling constants, and that's what alpha is, changing with energy density is not foreign to the mainstream physics community at all. So that we have alpha appear to be, now alpha might appear to be constant if previous measurements were conducted at a quanta density of approximately 0.237 of maximum possible density. Now, as a check, I did proton electron mass ratio in the exact same 7 files to get these 7 points here. And that was found to occur at about the same quanta density, suggesting that this density, and this is a very important point, may approximate laboratory conditions close to standard temperature and pressure, because I need to get the constants for temperature and pressure worked out in detail in binary mechanics. So that's the next step. So here is the graph. There's basically we've got 7 runs of the simulator, okay, and these are means and standard deviations, because over time the exact bit density will change when it's run in random mode, because bits are exiting and they're randomly injected with each tick to sort of try to maintain a constant quanta density. So that's why you get the horizontal variability here. The vertical variability, of course, is that seen in the new constant alpha definition I just described. And the red arrow indicates approximately where the alpha is. This is a regression line showing how nicely, with 97% of the variance of alpha, that's what R square would be, the percent of variance accounted for in this regression line is so that amount of variance of alpha calculated here is accounted for by quanta density. So if we move on down here, what we've got is just saying that some details about the methods. Now, one error in my presentation about 2 weeks ago on this subject was I showed this very same image here, and I had left out the decimal point. So instead of 3.5 million BMLS ticks equal to 1 attosecond, it's actually only 350,000. So that's just a slight correction there. So let's motor on down and end this, since some of the listeners here, I think, are going to be already familiar with what's been done. Oh, okay, I'm scrolling, but it goes slowly because I guess the CPU is competing with the browser in two different browser windows here. Okay, now it's too far. I'm trying to get it to go back up. It won't go back up. Okay, I'll just say it in words. Now, in this figure is what I just mentioned in the abstract section. The apparent dependence of the fine structure constant, as presently defined on quantum density, suggests that alpha may have appeared to be constant if previous laboratory measurements were conducted at a quantum density of approximately 0.237 of maximum possible density. Now, now the Wikipedia article we discussed several weeks ago gives the Hall effect, Hall, Hall effect, as one of the things used to measure alpha. And that is when a magnetic field crosses a conductor, a transverse electrical potential appears. That's the Hall effect. And somehow they're able to extract the alpha constant from that those measurements. Now, I mentioned that because it seems that most of the measurements of alpha actually are done at what might be called standard temperature and pressure. So the measurements of the proton mass electron mass ratio were also found to occur at about the same quantum density. And if I could get it to scroll, oh, there it goes. It's responding now. The red arrow here shows you approximately the 1,836 ratio of proton mass compared to electron mass. And you see there's more scatters, but these are the exact same 7 runs as were shown for the quanta measurement, that composite variable. And now it's not responding. I want it to scroll down. Okay, it doesn't want to scroll down. Well, let's see. Oh, there we go. So the similar values of quantum density for alpha, here we're at 0.238 roughly for the proton electron mass ratio, and we were at about 0.237. So they're very close. Is it a pure coincidence that these two values are similar, or do they suggest that this density range may approximate laboratory conditions close to standard temperature and pressure where these measurements have been conducted in laboratories in the past? Okay, and to conclude now, here we go. There's just a few paragraphs here of discussion. How simple is that? If the present operational definition of the fine structure constant is correct, excuse me, the present report may represent a happy ending to a very long story of heroic efforts by many investigators over decades to understand it. The fine structure constant definition presented is simply a composite variable of 3 event counts recorded at each BMLS tick. The M quanta prior, that's very important, prior to application of the time development bit operations, the M0 sub-0, scalar electrostatic events, S, and the vector magnetic events, V. In brief, alpha equals this little formula, the proportion of M quanta accelerated by electromagnetic events. Now, how simple can you get in terms of defining alpha in the context of full quantization in binary mechanics? Indeed, alpha appears to have been hiding in plain sight. M sub-0 is part of the system state called the bit function. S and V are events in the time development laws called bit operations which have been precisely defined mathematically. Hence, the alpha definition qualifies as a derivation from first principles. Remember, a derivation of these unexplained data, which physics books wrongly call constants. They're unexplained data. Can't use any other unexplained data. And if you notice in the foregoing, what I just presented, there is no unexplained data used. Okay, here we go. And then there was 3, as in the 9 Little Indian story. The value, oops, it scrolled more than I wanted it to. Let's see, will you go back so I can see? Oh, okay, let's stay right there. Here is our physical constants derivation tree. Previously, the only update here is we've got our 3 primary constants for the units of measurement in physics. And the only update here is that I was wondering previously if alpha was a 4th primary constant. Now I believe, no, it's not. It depends upon quantum density. It's simply a coupling ratio observed both in the Hall effect and other experiments, as well as in the binary mechanics simulator, as I just presented. Now, to keep, let's see, is there anything else here? Yeah, on the other hand, the 3 primary constants are thought to be invariant, along with those secondary constants, which depend only on the primary constants and not alpha. So here we're getting into, my friends, the take-home message. In contrast, the values of Planck's constant and the electron magnetic moment depend upon alpha, as shown up here. Like here, this one depends upon alpha. And therefore would be expected to also depend upon quantum density predictions, which experimentalists might well follow up on. In this constant elemental action A, which I defined above in the figure 4, would be deemed to be more fundamental than Planck's constant. How about that? Likewise, elementary charge may be evaluated as more fundamental than intrinsic electron magnetic moment. Here we have Planck's constant and the intrinsic electron magnetic moment, both depending upon alpha. So they must not be as fundamental as we might have thought previously. Now, the next punchline and last one is to keep physicists busy with additional predictions. Alpha may be plotted over the full range of quantum density from 0 to 1 as proportion of maximum possible density. This range includes perfect vacuum, the baryogenesis threshold, and it's described here. End of story. So in other words, in plasma, and there's a lot of work going on with fusion attempts in a plasma environment, for example, at Princeton Physics Department, trying to observe things there. What I'm saying here is that the alpha value is quite different at the plasma level, and have they taken this into account? Or can they confirm what I'm asserting here? End of story. Thank you for your attention. Now, I'll leave this screen sharing up for a moment in case there's somebody have comments about it.
Well, I think, I think that's interesting that there is this question as to whether the fine structure constant is actually constant. I mean, they mention this in the wiki.
Right.
They didn't provide any actual data, but they did say that, let's see here. The varying, I was wondering, did you have data showing that the fine structure constant actually does vary, or that the
Yes, that's the very first slide. Let's see, page up.
Well, you showed that it would vary in your simulation.
That's figure 1 of what I just showed.
But does it actually vary according to the mainstream? You have data there showing that different people have measured different values for alpha.
No, well, my data here is strictly from my own work in using the binary mechanics lab
Yeah,
simulator,
I know. I mean,
and
your
it
binary
shows a
mechanics.
variation of alpha.
Yeah,
Now, Main Street, uh-huh.
yeah, you're making that prediction, right? That's specific prediction of the binary mechanics. So
Yeah, and this is actual data here from the simulator, and it would make the prediction if other people could find environments in which quanta density is lower or higher, the value of alpha should vary. Now, whether alpha can be measured from incoming light from astronomical objects, I'm not sure of. But my vacuum composition paper shows that when you have a violent explosion of plasma, you wind up with a lower quanta density in that area. The explosion is so violent it just blasts the quanta out of the volume. Okay, and that's a phenomenon we call supernova. Now, whether there's some way to evaluate alpha based upon light coming from those astronomical events, um, that would be perhaps a supernova down here, and the alpha should be less uh, for that situation. So it's sort of like I've just thrown the predictions out, and that makes binary mechanics very, very vulnerable because someone could say, okay, let's check this prediction, and I figure out a way to do it, and we're going to confirm the binary mechanics prediction, or we're going to raise doubt about binary mechanics as a whole, actually, since all of this is based upon the same basic postulates of full quantization. Does that help, Franklin?
yeah, I mean, I think that's a good characteristic for your theory to have, which is that it makes a testable prediction. And if you can manage to, at that physics lab who's working with plasma, measure alpha in that environment, and it comes out to be significantly different, then you would have, your confirmation or your denial. So, but
Let me throw out something here that someone can beat me to it. One reason I'm concerned in this little presentation today with what I'm calling standard STP, standard pressure and temperature environments, such as at sea level approximately, or in our laboratories and so forth, approximately 273 degrees Kelvin is our normal room temperature range. Is that with the simulator, we can actually count the number of quanta lost when you cool the simulated volume down to absolute 0 Kelvin, because all the quanta representing kinetic energy and particle motion have left the volume because we're running it in vacuum mode, which means we don't replace quanta that are leaving the simulated volume. So we know how many quanta are leaving when we cool to absolute 0. If this bit density range that is shown here by the red arrow is in fact our room temperature kind of STP environment bit density or quanta density, then we might be able to calculate the Boltzmann constant, because we know the amount of energy lost, which is the number of quanta lost, comparing the initial density to the final density at 0 Kelvin. And we know approximately the room temperature that's going to give us a span of about 273 degrees. And so the ratio there should be the Boltzmann constant. Now, who's going to beat me to it? Because that's my next paper. If you beat me to it, you have the simulator, you can do exactly what I just described and calculate the Boltzmann constant. Does it work out right? And if it did, I mean, that would be sensational result.
let's see. Lucifer has a question for you. Is the time one of the constants there? How can any amount of time be a constant? If you manipulate the frequencies, flow of time changes.
Well, actually, the time is a unit of measurement, and it's quantized in binary mechanics. I'm not sure exactly if I understand fully the question or the query. So it's just quantized, and it turns out that making you see, someone might say, and I think even Franklin has mentioned this in the past, and it's a legitimate point to make, by the way, Franklin. Let me see if I get that updated constants tree back up here. I'm trying to page down to it. Okay, getting there. It doesn't respond very fast because I guess it's competing with CPU time with the other stuff. Now, where do these constants come? Okay, there's time. It'll hopefully eventually scroll down. There we go. It went too far. You press the up and down arrows too many times, and then it scrolls more than what you want when it finally gets around to doing so. Oh, okay, these three constants, where do they come from? Were they just made up? What I'm saying is that for the mathematicians in the world, these are the only values, period, end of story, that's going to get you all of these measured so-called fundamental constants. Oh, okay. A good mathematician could even prove that. So that we look for consistency, right, left, up, down, every which way in this tree. And when it's all consistent, those are the values that we have for full quantization right here.
Well, I think perhaps he's getting to the whole question of whether time perhaps can be quantized, because you would think that any segment of time could be subdivided into something smaller, or he's mentioning that you can manipulate the frequencies. And I think that, to answer his question, I would think that one of the constants is time. And the way that amount of time can be constant is because it represents a smallest amount of time in which any observable action can occur. So in the chart here, that amount of time is like 7.14 times 10 to the minus 24 seconds, which is a remarkably small, short amount of time. So
right, we were saying that 350,000 BMLS ticks would get you 1 attosecond, which itself is a very short amount of time. Now, what Franklin is saying is something which I think is very, very important. These constants here apply to the level of analysis that physicists currently have concerning what is the value for elementary charge, what is the value for Planck's constant, the speed of light, electron mass. When you look at the bit operations, the time development laws of binary mechanics, you have to start to think that in order to do any of them, whether it's the unconditional bit operation, the scalar or vector bit operations, or the strong, there's the 4 of them, there must be a series of steps which have to be implemented in a certain order in order to implement those time development laws. So that going beyond binary mechanics and this level of analysis, if you will, we might have in the future a further breakdown of time into even smaller quantized units to represent the individual steps that have to be implemented by the spot units, of which the universe appears to be made, composed of, in order to implement those. And the same thing with length. The length is the size of a bit locus, but there may be mechanisms within a bit locus required to implement the time development laws. So in a way, I believe that Franklin has pointed us beyond binary mechanics and pointed out that, in fact, these constants here are called primary constants only with reference to what physicists now call the fundamental constants: electron rest mass, light speed, charge, etc., Planck's constant. But those aren't fundamental constants as far as I'm concerned. They're simply unexplained data. And binary mechanics, by the way, is the only theory that I know of that has even made an attempt to explain that unexplained data or account for it.
He's got another comment here. That amount of time has to be related to a certain amount of some cycles. I think real constant is a single cycle of some elementary waves and the speed of these waves travel. The rest is harmonics. So that's a little bit difficult to understand, not complete English. But
well, the minute you say harmonics, if I may chime in here, you're starting to talk about real number math, okay? Where position can take real number points in space, as opposed to integer coordinates. Time can, must be infinitesimal increments in time must be allowed in order to do the calculus and what have you, to analyze pendulums and other harmonic oscillators. As a matter of fact, all of what I call legacy quantum theory prior to full quantization in binary mechanics is based upon this harmonic oscillator idea. It's just over and over again. They just go back to the same idea and they never get anywhere. And not a single one of them has even derived why light speed is the value that it has, or electron mass, or elementary charge, or any of these constants. So they've all failed. And I would like other people to start to work on this, either to confirm what I'm saying or to participate in making advances in physics. Because right now, binary mechanics doesn't even have a close runner-up as far as the physical theory goes. There's not even like a close contender. It'd sort of be nice if there were a close contender. Then we'd have some real competition. But right now, there's nobody who can do much of anything.
well, I
And
don't
that's
know
an editorial comment, which you might say is biased, and I would accept that if you were to say that.
I'd say that's a little biased.
Okay, yeah.
That's perfectly fine. I mean,
What do you, of course I'm going to be a little biased.
That's fine. I could say though that my theory, I don't have this kind of level of detail. Like, I've not worked out, what the time constant is to, 6 significant digits here. But I take, my stick is a little bit more different. My stick is more intuition, more billiard table stuff, I would say. So I'm kind of come up with the picture of what's going on. Although you also have a picture of what's going on, so you can actually see it going on in your simulator when it's running, but you can't see it as in terms of like there's actual billiard ball, and that's what a thing is made out of, and how.
Well, that's correct. We need some real software wizards to assist in developing further both the simulator and how it displays what's going on, as well as the ability to take the saved files of the simulated volume, what I call the bit function, the actual bit distribution in space, and analyze that. And we're working on that as well. If you press the P character while the simulator is running, it'll just show the protons. And is it a rather crude definition of a proton in terms of number of quanta? Yes, it is. But we need to get in there and analyze these files. And anyone who's interested in analyzing them, heck, just email me and I'll send you the format so you can read these files in whatever software language you like to program in. And then you could go through and say how many proton or nucleon particles are right next to each other. If there are none that are exactly right next to each other, maybe all of them are hydrogen nuclei, protons in other words. Or you find groupings of them. Say, here's a helium atom because I've got that grouping. Like when Franklin shows his Lego block model of the different atoms in the periodic table. Well, the volume simulated can be analyzed, and that's the .s and the .mat files. You could just go in there and start to analyze them and write the software to do so.
Yep, that's possible. So that's your update on the alpha. So you have
I'm sort of done. Yeah, I don't want to monopolize the time here.
And so you have a question on like when you consider the action starting from the beginning rather than the end. And you've made some predictions about the value of alpha being variable. So I would say, James, that evidence might already be out there. So I think you should go ahead and look very carefully to see what all the alpha experiments are, and to see whether there is some definite different numbers being measured, because that definitely is what happens with trying to measure the gravitational constant, that everybody has equally valid ways of measuring the gravitational constant, but everyone comes up with a different value. I mean, it's not a matter that their error bars are off. They are just simply different. The same kind of thing, let's see here, that like the measuring the neutron decay rate. That's another example where this thing does not actually appear to be constant, depending on how you look at it. The value.
Right, I agree with that.
So just I would do that. See whether you can find all the experiments on alpha and see whether you can find anybody actually saying that they've come up with like two values close to each other but incompatible. See, so that would
exactly
be, any evidence of that would support your contention, what you've seen in your simulator, that it should actually not be a constant. That's kind of the new thing. You've decided that alpha is not a constant. It's a function of bit density, or should be.
And furthermore, that Planck's constant is not a constant, an intrinsic electron magnetic moment. In fact, I would guess that any magnetic moment of any particle that people are measuring, if they can figure out how to measure that at different bit densities, that would be very interesting. As far as the astronomy goes, as I mentioned, my vacuum composition article strongly suggests that the incredible explosions in what we call supernova leave behind a volume of space which has a lower bit density. It's just because the explosion is so violent. Quanta are just extrude or blasted out of the volume with incredible energy. So that it could be that if somehow alpha could be, or Planck's constant, or even magnetic moment, those values which are known to depend upon alpha, according to my derivations of them, and also formulas in the literature, that would be an interesting confirmation. On the other hand, whereas the supernova explosion volume may give you in the aftermath of it, an area of lower quanta density, we should get a lower quanta. How about energy coming from a black hole? That would presumably be a higher quanta density. And so the value of alpha could be higher, according to this analysis. So that
I wanted to ask you
my problem
about you mentioned magnetic moment here, right? So you have the concept of magnetic moment in your system, correct?
Well, this is calculations done based upon the classical formula for magnetic moment. And in other words, both for Planck's constant, I use the classical formula for angular momentum. For magnetic moment, I use the classic formula for that, which is the current circulating around an area. That's your classical formula for magnetic moment. And I was able to derive the intrinsic electron magnetic moment using other constants like the length constant, the time constant, and electric charge, which was previously derived. So it's a derived value now. And fourth, the value of alpha is required to get the proper value. And so that is how I got, not from running the simulator, but actually from just a calculation. It's just an algebra exercise, basically.
So you have the intrinsic electron magnetic moment in your chart here, and you're saying that's derived from, and you've got arrows coming out of the elementary charge, and you've got arrows coming out of the elemental charge. Now, ultimately, the intrinsic electron magnetic moment is, just some number here.
It's just a number, and if you use the classical formula that I cited, which is the current around a given area, we know that according to the binary mechanics model of space, that the quanta in the electron spot circulate, and we know the diameter of that spot, or the radius in which the quanta circulate. So we know the area, we can plug that in. We use our length and time constants as required in that classical formula, and we get the magnetic moment of the electron. So that's purely an algebra computation. There's nothing about the simulator there. But the point that I would like to make is, how could it be that these two values of length and time, see the arrow goes all the way down and all the way down from time, give you the correct value for electron magnetic moment, and also the correct value for light speed. Anywhere else they go down to elemental action, and finally to Planck's constant. How could these same values be appropriate and give you very precise results for all of these different values of unexplained data? I will emphasize. The big argument that someone could make against this work, against this derivation tree, is that, it's just one huge colossal coincidence. Oh yeah? Well, good luck on that. Because while you're wondering, is it a huge colossal coincidence, I'm going on to try to derive from these same values the gravitational constant, capital G, as well as the Boltzmann constant, which relates temperature to energy. So, like, my problem here is that one person can't, with a comprehensive theory like binary mechanics, which is supposed to account for all known phenomena, how can one guy be sufficiently expert in every possible subcategory and subdiscipline within physics? It ain't going to happen. That's why different people with different mathematical and specialties in different areas of physics, like I mentioned, astronomy, with respect to looking at alpha at different quantum densities, whatever, are needed to sort of get on the train of what appears to be the winning horse in the whole game of advancing 21st century physics.
Now I was curious, so in your calculation, the intrinsic electron magnetic current, the presumptions that you made was that there is an electron, it's basically going in a circle. Is that right? That's how you tried
if you cool down a simulated volume in vacuum mode, which you just let all the bits that leave it, they don't enter again. So eventually there's no more quanta left to leave it. and there's no more kinetic energy. In fact, there's no motion of any particle whatsoever within the simulated volume. The only thing moving is the quanta in the proton and electron bit cycles. And that might be called our 0 point energy as far as perfect vacuum goes. Now, at perfect vacuum at zero, well,
I
atoms
just want to
at
know what is your basic, how did you come up with the calculation? What was your presumptions there? I mean, you're saying that,
okay, well,
that this was not actually anything that needs to be directly derived out of your model, that's something that you can directly derive out of basically the constants. But you had to have some kind of model to what you're calculating. So what was your assumption?
Yes, well, the model of space showing the quanta circulating with a radius of about 0.8 L is the radius, okay, and they circulate in a circle. Excuse me. That model, there's your model of the space. Okay, that model, we applied the classical magnetic moment formula at current around an area, because as I just said, we have the radius, so we have that area. Okay, what about the current? We have the elementary charge, which is the value here, going into the algebra there, and the length and time constants are also used. And it turns out, if you go to the paper on this subject, there's a whole paper just on this, so that those who are interested can just go to the paper on intrinsic electromagnetic moment, and you'll see what the algebra is. But basically, it's the model of space, which gives us the radius of the charge circulation. We have the amount of charge involved and circulating, and we have the length and time constants required to put all this together using the classical definition of magnetic moment, and there you have the answer. It's right there. So that the simulator itself was not used; it was just the published model of the physical interpretation of binary mechanical space.
All right. So I was going to discuss the whole topic of magnetic fields here. So seems that we have already intersected that particular topic here with the discussion of what
Wonderful. So I'm going to stop sharing.
Magnetic moment is. So, it seems that that's, first of all, just a kind of start there. So if we go back to the wiki explanation of a magnetic moment here, is that basically anything which is emitting a magnetic field has what is called this magnetic moment. And so it'll have like a north and a south. It has a direction, and it has a intensity strength. So I'm not exactly sure how they get, like, for the intrinsic magnetic moment, how that could all end up to be like the number 2, which I think apparently it is. That doesn't exactly make sense to me. But, examples of things which have magnetic moments include loops of electric current. And, that sounds like what James had basically started with, which was you have a charge, you have a loop, you have a radius, and you can make calculations on what the magnetic moment would be for such a current loop. But in addition to that, we have permanent magnets. We also have moving elementary particles, such as electrons, various molecules, and many astronomical objects, such as planets and the moons, the stars, etc. So even the planet Earth itself, has this magnetic moment. So a lot of things have a magnetic moment. Even atoms have magnetic moments. But the real question is how does that magnetic moment affect other objects in the vicinity? So it's like the simplest example of a magnetic field affecting something is that if you have a particle entering into a magnetic field, it will not continue just going straight along its own little happy way. It changes in direction, right? It is deflected. So that's a very basic, fundamental physical thing that happens. So my question would be, say, to James is, what is your explanation for why is it the electron does not continue plowing straight ahead when it goes by one of these magnetic fields? I mean, it's not crashing into something. It's relatively distant away. I mean, that particle be like 1 foot away from the magnet or the wire coil. It would seem to be very far away, but yet you can see the influence on that electron. So I was wondering, James, can you comment on what you think is going on there?
Well, the short answer is it's called the vector the vector bit operation. Okay. And in binary mechanics, the L-type bits can act as a magnetic potential when adjacent to an M bit, which is your charge attribute quanta type. There's only two quanta types. And that acts over a distance of L, which is the fundamental length constant. That's how far they are apart in the binary mechanical model of space. So that's the quick, short answer. In other words, anything whatsoever. Franklin mentioned an electron in the magnetic field, but it could be anything. Is going to be affected by the one of the four bit operations for time development, namely the vector bit operation.
But how's that explain these long distance effects? I mean, I've got one spot
well, the long distance
that's an electron, and it's going, in a loop over here, 1 foot away, which is like in binary mechanics, it might as well be 1,000 million miles away. We've got another electron, and it's being affected. I mean, how can this thing happening over here get all the way? I mean, I could understand that maybe on an individual basis in something that's right next to something that it could be affected, but something that's like, could be.
Okay, well, Franklin has raised this issue before, and I have to thank him for doing so because it has made me think. Now, when the vector potential in just one instance of it in a simulated volume accelerates an M bit, now the M bit is in a different location with implications for future cycles of application of the time development laws. Okay. Now, I have found that a number of parameters, you can look at the CVS file, you just click on it, CSV, .csv file that the simulator produces. And if you double click on it, if you have a default spreadsheet, it'll just load. If your spreadsheet will do plots, just click tick, which is the first variable, and any other variable, and plot it over the whole time. You will see that in some cases, it may take thousands and thousands of ticks before things stabilize. Now, that particular variable that you're looking at. Now, what does this mean? And again, thanks to Franklin, because I was starting to think about what does that mean? It means that every single time a bit, a single quanta changes location, even by distance L, that has ramifications that ripple through the entire simulated volume, and it has entered a whole new state. So that single bit motion based upon a quantized time development law, the vector bit operation, again, can have effects over any distance. And yes, those effects would be at the speed of light in terms of their delay. And there's where you get your R squared law and so forth. And by the way, one can use the simulator. I have this on the agenda to show that the R squared law actually can be demonstrated with the proper setup of a series of experiments with the simulator. Okay, so that's my response and I thank Franklin because he's raised this question several times and has caused me to think about it. And that's basically what I think is happening. And I've come to appreciate, at first I was a little disappointed. I was saying, oh my God, how can I get stable values for some of these parameters, which the simulator records in its output .csv file. And, because in my simple little mind, I was expecting that things would be simpler than maybe what they actually are. And it occurred to me looking at long runs of 10,000, 20,000 ticks or more, which is still a fraction of an attosecond, okay? That even a single reconfiguration of the quanta in a volume has implications that may take quite a while to be that to restructure based upon what that particular change is.
Yeah, you're cutting out a little bit there, but I think it's important that we recognize that
a little change here, the whole so-called butterfly effect, can cause a huge restructuring of the whole thing, given the sufficient time for the.
Yeah, I think it's important to recognize that there is a restructuring, even though there's like this local thing going on. Like you have a coil of wire that's very local, that it's causing some kind of restructuring of the space around it, such that when the electron encounters this restructuring, it has to go a different way, right? That's fundamentally what the magnetic field is doing. You have to somehow account for the fact that there is this other different force. It's different from the electrostatic force. So if you measure the electrostatic force around the coil with the electrons running in it, you'd find out that there is no electrostatic force. It's not like it's still neutrally charged. There's no net positive or negative charge coming out of that thing that causing the electron to deflect. I mean, that would be another thing that would cause an electron to deflect. If I had a big old just positive charge, the negative charge would be attracted straight to it, and we would, of course, expect the deflection to happen in that case. But even in that case, we still have to think that the charge is also somehow influencing the rest of space. And, the electrostatic force is infinitely ranged. So even a single electron here in Seattle is still affecting some electron, 3,000 miles away in Boston to some extent. So, how does that happen?
Like, for example, a single bit change in position, and of course, many changes occur in one cycle of the 4-bit operations, which comprise a simulator tick. But even a single one can have ramifications at any distance up to infinity down the line. And the only thing that I would say, and by the way, this is contradicted by people who think that certain quote unquote forces or influences like gravity might be instantaneous or faster than the speed of light. And there are some very smart people out there which do think that, and I would like to ask them, what really is the specific experimental, tangible, that I can touch evidence that there's effects faster than the speed of light. In other words, action at a distance faster. But now in the Coulomb's law, derivation of electric charge, I quantized the Coulomb law. R square in the denominator just becomes the length constant, L squared. And so there is only one force. And using that simple quantization of Coulomb's law, I derived electric charge. I mean, it's almost embarrassing how simple this stuff gets. Okay, now and that's a benefit of full quantization. And then you say, well, what about the R square value of 1 meter, or 100 miles, or whatever in Coulomb's law? Well, that quantized Coulomb effect that occurs in not the vector bit operation now, but now I'm talking about the scalar bit operation, the electrostatic one. That motion of that acceleration that it does of m bits when that occurs has ramifications which transmit throughout any distance according to the general R square law that we use at a more macroscopic level in terms of application of the Coulomb's law. Okay. But as far as my work goes, it's no mystery why these effects.
I don't want to interrupt you too much, but let's see. So Dennis has
please do.
Dennis has put in a comment. So he said that he would like to discuss a new magnetic experiment. So Dennis,
wonderful.
Dennis, yes. There. Let me.
Franklin, before I ask that, though, I got a quick question for James on his model, and I'm just going to send it now.
Okay, it says, James, in the electron magnetic moment, how much charge is circling at any time, and what is the charge linear velocity at any time? Okay, so those are two reasonable questions based upon the model you're based upon. So how much charge and how fast?
The amount of charge is each M-type quanta, and there are 3 in an electron, because there are 3 spot units, and each spot unit has 1 M-type quanta and 1 L-type quanta. So the amount of charge is given there. That's the answer to the first question. And as far as the linear velocity, excuse me?
I mean, did you really answer that? I mean, I think he might be asking, or like I would ask, like in terms of standard charge amount, is that the same as what we observe in, say, a single electron, or is it like a third of a charge? How much is the charge?
Well, each M quanta would be what I'm calling an elemental charge C. And 3 elemental charges make up the full electron charge. In physics literature, this is also called a fractional charge. And I don't use the term fractional. I use the term elemental charge simply because the term fractional charge is also used in other contexts in the literature. And to avoid confusion, I just give it a different label. Because so all these words we're using are merely labels for the mathematically defined entities in the work.
So is it 1/3 of the charge that's going around in a circle?
Well, if the 3 M bits in an electron spot, and there are, the total amount of charge going around in a circle would be elementary charge E, that you can look up in Appendix A of almost any physics textbook.
So that
and
is
which I derive.
That is the charge of a single electron.
Yeah.
And what's the velocity?
So the answer is
the velocity is given by the length and time constants, and that can be calculated. Like since they're going around in a circle, you have a vector situation. And so in order to get the linear velocity, it'd be one component of a vector. And go ahead and do the calculation. I mean, the numbers are all there in my paper.
Yeah, apparently he has a whole paper on just this. So
But I don't think most people can read your papers very well. I know I can't. What is the velocity? Is it c, for example, the velocity of light?
Nope.
okay, it's something that I
Oh,
suppose
okay. There are 6 ticks, which 6 simulator ticks. Let's see. There's okay. There's 3 simulator ticks. Each simulator ticks is time t. Okay, the primary time constant. You can calculate the circumference of the circular path that the m quanta are following, and so there you have a length. You want to know the velocity in that circle? I'm just giving you the length. Now, how about the duration? A single m quanta completes a cycle in 3 simulator ticks. Each simulator tick is 4t, where t is the primary time constant. Why 4? Because we're assuming that each of the 4 bit operations elapses or requires, or the duration of each one is the same amount, and it's t. So there you have the time. Divide the 2 values, and you've got your velocity. I don't think I've done that yet, but you know, I could whip out my spreadsheet sometime and get back to you as to what that velocity actually is.
Yeah, I'd like to know what it actually is, not in terms of your ticks or anything, but, meters per second.
Well, that's what velocity in my work is. Remember, we've quantized the units of measurement in physics. So everything that we have to say about velocity or anything else is in meters per second.
James. I understand that, but you should be able to, if they're circulating, and they should have a linear velocity, and you should be able to calculate it in meters per second and get back to, because you want other people to check your results. Well, they'll check your results in meters per second, not in ticks.
Well, that's fine. I'll do the calculation and send you an email of what I get.
Thank you.
Okay, so Dennis, you had an experiment you wanted to discuss.
Yeah, I was talking with a friend of mine, Andre Michel, over on ResearchGate. They have questions that you can answer, and then other people answer them and get back to you according to your answers and whatnot on ResearchGate.com. And we were discussing gravity and anomalous effects of gravity. And someone chimed in, and I didn't note his name, unfortunately. Someone chimed in and said that one of the anomalous gravitational effects is that if you drop say a ball bearing on the floor, made out of iron, then the weight decreases, and then gradually over a short time goes back to normal. So I didn't believe that could be true at the time, but it stuck in my mind because it would be an easy experiment, as the guy said, to perform. And so after I thought about it for a while, the other day I got the idea that, as you know, I mentioned this before, I've characterized gravitational mass and also inertial mass, which is different. Gravitational mass is the electrostatic, corresponds to the electrostatic energy of an electron or a proton or a neutron. The electrostatic energy over all space, inside, on, and outside the particle, divided by c squared, because E equals mc squared. And so it occurred to me that whereas the gravitational mass or the inertial mass is a Lenz's law effect, where Lenz's law is that if there's a magnetic effect, a sudden acceleration or something, then there's a reactive magnetic counter field. And Lenz's law is one of Maxwell's laws, but when the Heaviside beat dead Maxwell's equations, he left it out. Anyway, so when this ball hits the floor, there would be a shock wave and a tremendous spike in the magnetic field at that point. And then after the collision, it would gradually taper off and you go back to the normal inertial mass again. Now, inertial mass is resistance to force. So that means if the gravitational mass remains the same and the inertial mass increases, the weight on a scale would decrease. And so it appears that my characterization of gravitational mass and inertial mass yields this effect of when you drop, say, an iron ball on the floor, there's a spike in the magnetization, and then the iron ball being a ferromagnetic substance, and then this tremendous spike in the magnetic field due to the Lenz law counter magnetic effect would line up the domains inside the iron ball and magnetize it temporarily. And then we know from ferromagnetic hysteresis that it would gradually decay. So I've been approaching various people to see if I could get them to try to perform this experiment and see if this guy knew what he was talking about who chimed in when we were discussing gravitation on researchgate.com.
Well, that's interesting. I've never heard of that. So you're trying to get someone to do this experiment where you drop a heavy iron ball, and when it hits,
well, just say an inch in diameter. It wouldn't have to be terribly heavy.
You drop it, and then somehow you measure a change in its behavior. As far are you talking about the actual scale weight being different temporarily?
Yeah, the weight on the scale would go way down immediately after the shock wave passed through the ball bearing, but then would gradually go back to normal because of a hysteresis type effect where the magnetism would decay over time.
Well, how would you measure the weight of a ball that's hitting a surface? I would think that would be...
Well, if you had a hard piece of plastic you could put on an electronic scale, and you could drop the ball on the piece of plastic, and it's the weight would be the weight of the register minus the weight of the plastic that it was dropped on. The only problem with this is that I can't find anyone, including myself, who has a scale that wouldn't oscillate for a while before it became to its final reading. One needs a scale.
That's the problem I'm seeing. Is that in order to measure the weight of something, it normally has to be, static, not, moving. That's...
Well, if you dropped it on the plastic, it would just bounce a little bit and then it'd come to rest if it was, perfectly flat. And that would give you, but once it comes to rest, if you could get an instantaneous reading, then that would be what would be needed.
Yeah, I think that's the other problem, is that all of these scales take a finite amount of time to take an accurate reading. Anything that's bouncing around, it has to stay on the scale for at least half a second or something, per se, for the mechanisms to kind of catch up, right? Because these things are basically strain gauge or spring. There has to be some time for that tension to build to its maximum value. So very difficult to figure out whether you're getting a a difference. Now, I could totally understand that a magnetic field impact would impact the weight of something. You could do that trivially by if you took a steel ball and you stuck it on a weight on a scale, and then you put like a magnet above it, you would see that, yeah, the weight is coming off. I mean, it could go off to like, zero if when the piece of metal is attracted to the magnet completely. So that is certainly some kind of effect that could happen. Or there's probably an interaction between the magnetic field of the Earth and any magnetic field you produce here on Earth. I mean, even if you took probably just any ordinary magnet, you would definitely see there's forces on it. I mean, there's definitely forces that will cause it to align north-south. That's how compasses work, right? We observe compass needles.
Right, but Franklin, the thing is, this is a self-magnetic field. It's operating on itself, and so if you believe in conservation of momentum in an isolated system, there shouldn't be any effect as far as the scale is concerned. But according to this fellow, anyway, there definitely is, and even if it only took a half a second to get a good reading. See, my scale takes like 2 or 3 seconds to get a good reading. If you had one that was like, you could get a good reading after half a second, that'd probably be sufficient to check this out.
Well,
Dennis,
I'm thinking.
Can I chime in here with a crazy idea?
Sure.
Yeah.
What if the experiment was completely enclosed in a la some of Dmitriev's work in Russia? The ball and the plate, which is below the ball, is encapsulated in a container, and the ball is held by a mechanical mechanism, and we could push a button outside to release the ball so it falls. And then we say, let's go backwards in time, and we're going to use a spring scale, and we're going to record with a very high frame rate camera the readings on the spring scale of this whole assembly, the whole experiment. The ball being held mechanically by our little holder, which we can release electronically by pushing a button. Its fall, it's hitting the plate, and afterward, it could be that this ancient technology of you using a spring type balance instead of the electronic one, we could then take the data and do the root mean square of the oscillations, which you say is probably going to occur when the ball impact occurs. And we plot that. Has the weight of the entire assembly, the ball and the plate, before, during the fall, at the moment of impact, and afterwards, we do the root mean square and plot it. We might be able to detect an actual change in weight. How about that?
Well, the change of weight is a function of time, though, because it gradually decays due to hysteresis type effects.
That's why you're going to record with a very high frame rate camera the reading on your spring scale. And you're going to analyze that data, put it in a spreadsheet, do the root mean square of the oscillations, and see if there was a weight change of the entire assembly at the point or near and thereafter the point of impact. So that it could be, all I'm saying is get rid of the digital scale and use an old-fashioned scale.
Yeah, here's the thing, though. A spring scale oscillates before it gets a final reading. It's according to Hooke's law.
Well, we're not interested in the final reading. We're interested in the reading at the point of impact. So we're going to take that oscillated data, put it in a spreadsheet, and calculate the root mean square, the average of those oscillations, and see if there's a dip. If there's a dip in that curve after that data processing, that would indicate in real time, as it were, not waiting for a reading after the fact, but actually during the fact, well, during the whole course of the experiment. Release of the ball, it's falling. The point of impact, we can get a measurement at all of these times within the resolution of the oscillation of the spring scale.
Yes,
In
but,
other words, you calculate a straight line curve fit to the root mean square of that oscillating curve. Is there a dip?
Yeah,
if there's a dip, okay. Go ahead, Dennis.
Here's the thing: if you the minute you push the button and release the ball to fall, the weight of the ball would no longer affect the weight of the rest of it. It would be in free fall. So you start out with the wrong reading. When you push the button, you immediately get a bogus reading as far as we're concerned. Then when it hits,
you plot the whole thing. It might
I
be
understand
surprising.
that. Let me speak. And then when it hit, the impact would not represent the weight. It would represent more the inertia, which is weight is gravitational inertia. Inertia is magnetic. Lenz's law magnetic. So as soon as it hit, the impact wouldn't tell you much either, at least as far as what we've discussed is concerned. Then it would start to bounce. Unless, of course, you put some stickum on the bottom of the ball or something like that. And the spring would start oscillating according to Hooke's law. The whole thing isn't a good idea.
Well, I had another different idea for you, Dennis. And this also has to do with using a high frame rate camera. And my idea is to get rid of the scale entirely. What you want to do is that when you drop the ball, it's going to hit that surface and it's going to bounce up somewhat. So you want to get some surface that you think this works on, but allows you to observe how high the ball bounces up. Because how high the ball bounces up will be dependent upon the mass of the ball. So you could, use your steel ball, and then you compare it against another ball which is made out of non-magnetic material, like some combination of lead and copper or something, which you try and make exactly kind of the same as the steel ball, but that's still not completely accurate. But what you would want to do is then observe to see whether the ball, which is not supposed to be non-magnetic ball, that jumps up, not as high as the magnetic one, right? Are you saying that the magnetic one loses weight or gains weight?
It loses weight, and
So
then it gradually regains it.
If it loses weight, then the rebound should be higher than the same.
But there's two kinds of masses. There's inertial mass and gravitational mass. They both come into the picture. The gravitational mass tells you how hard the gravitation, what the force on the object is due to gravity. That's what gravitational mass. Now that doesn't change because it's electrostatic in origin. But magnetic fields have the Lenz's law effect, and they do change under impact. Now, I think your idea is dropping a magnetic and a non-magnetic one. But remember, the Lenz's law works even for non-magnetic materials as long as the electrons and the protons are electromagnetic in nature, according to the Bergman-Allen modeling. And so there would still be a Lenz's law effect, which would be responsible for the inertial mass, but it wouldn't line up the electrons in the substance because it was non-magnetic. So your idea of trying a magnetic ball and another one which was about the same, but made up of non-magnetic steel, say with vanadium or chromium, seems to me to be a good one, because there should be a difference in how high they bounce. But the problem here is the modulus of elasticity comes in too, and that depends on exactly how much what the material is made out of chemically, and so that's another. That's why just dropping the ball on a scale and as quickly as you can, measuring the change in weight, if any, would seem to be a lot simpler to analyze and to perform than the one you mentioned. Although what you mentioned, Franklin, was actually a pretty good idea.
Yeah, there is that. And that's why I was thinking that you couldn't come up with a magnetic, non-magnetic ball. But maybe what you could do, you could come up with the ball which is just not magnetized, and then you could come up with a ball which is super magnetized. Certainly you could do that. You could have a demagnetized and magnetized ball. Now, I'm not sure in your theory, whether that would be the same difference between because all you're looking for is some difference, right?
Yeah.
The magnetic magnetized, a highly magnetic ball is different than.
Well, you don't want the ball to be magnetized, just be ferromagnetic in nature. If it's magnetized, that throws another spanner in the works, so to speak.
Yeah, that would be. So that would be that's why I was wondering whether that would be throwing your experiment off, that it's actually magnetized, right? Because maybe if
temporarily until it decays due to hysteresis effects.
Because you're effectively saying that the ball may start out unmagnetized, ferromagnetic thing. It hits the ground, it becomes magnetized.
Yeah.
And it comes back up, and you could possibly measure that it weighs less, right? By some tiny fractional amount. So.
Well, it shouldn't be all that tiny, I don't think.
They don't think? They would think
No.
it would be vanishingly small. I would think that. First, you would probably need to see whether a magnetized ball itself, that's definitely something you could do. You could take the magnetized versus the unmagnetized ball, and you could see whether, the magnetized ball should actually weigh less than the unmagnetized ball, I guess, because that's what you're presuming, is that the change in magnetization causes a change in weight. So I would think that you would be able to trivially that right out of the bat, right? Just take
But it's not the gravitational mass that changes, it's the inertial mass.
And that should be the case between a static unmagnetized ball versus a fully magnetized ball.
If it was magnetized, then you'd have to take all the magnetization, because you can't have spherical magnetization. It would have to have poles. And if it had poles, then you'd have to worry about what their orientation was with respect to the vertical and so on. I'm not saying that this is a bad idea, but it's complicated, a lot more so than just a simple experiment I mentioned.
Yeah, I mean, that's an interesting topic. I mean, this is how science is done, as like you've got this hypothesis that the weight changes on ferromagnetic materials when they hit the ground. And then the whole question as an experimentalist is, well, how in the heck do you do that? How do you prove that? And what are the problems? Yeah. And so that's that's exactly the scientific method that we go through. And that makes it an interesting question to ask about. Yeah, how are you going to measure the weight of something that only changes weight just fractionally and only does so for a short amount of time?
Yes.
How short are we talking about here? If it retains its properties for a couple seconds, then what you can do is that you can just drop the ball and then immediately put it on a scale and see if it weighs different, right?
Well, you could drop it on a scale and let it, then we wouldn't have to.
If it stays magnetized long enough for the scale to settle, then you would be able to measure that directly. right?
Exactly.
So it's just a matter of how long it takes for the scale to settle and how long does it take for that ball to be demagnetized.
Yeah.
So you might still be able to do it. You still might be able to just drop it on the scale and get the weight. If you get any difference in weight, then that would be a positive result.
That's
Then
right.
but if
It
you
should be
drop it
less
on there
weight, not
and
more weight.
it every single time, it weighs exactly the same as when you didn't drop it, then that would be a negative. So you could do that simple experiment. Just drop it and see whether you see any difference between that and when you just stick it on the scale. You know, after an hour after you do this experiment to make sure that it doesn't have the residual magnetization. Or you can get a demagnetizer thing. You can make sure that there's nothing magnetized on it, and then just measure it. But you know, if you have a super high precision scale, you might get something, maybe. The amount and types and accuracies of the equipment that we have available to us from eBay is like fantastically much better than anything that anyone has had in like the past 100 years. So we can do things like we can do fine gravitational measurements with just like my cell phone because it's got a gravimeter in it that's accurate to like 3 or 4 digits, right? I did this once because I was trying to do an experiment to see whether I could tell the difference in gravity between the ground level of my building and like 20 stories up at the very top. And the problem there is that the force of gravity, according to the gravimeter in my cell phone, it varies quite a bit. You see that, and it's just it is bobbing up and down, just sitting there. So it's a matter of when you take it up 20 floors high, is that bobbing the average rate, different than what it was down below? But you're definitely not getting a single measurement at any particular height. You kind of have to eyeball it and stuff like that. But I'm just saying that it's the amount of the experimental types of instruments that we have available to us is actually a lot more accurate. And just like us having the internet, that we can go and even as we're discussing here, we can go on a Wikipedia or any research paper and just instantly look at it. That's something that would have taken someone hours to do in a research library, and they might not even be able to find the answer because not everything is filed away in the library that you happen to be in, versus the internet where everything is absolutely available from everywhere, all across the entire earth, from every single nut job who wants to put something on the internet. So that's a big difference. Let's see here. So that's an interesting experiment. But let's see. Let's get back to the original topic at hand, which was the magnetic field. And we had begun to discuss what are some of the properties that the magnetic field is created by, say, like in the simplest way, by current with electrons flowing through it. That I would say is probably the simplest kind of magnetic field that can be generated. I mean, you don't even have to have a coil. All you have to do is just have a straight wire which you run a current through. And that generates a magnetic field. I mean, it generates a magnetic field such that if you put another wire next to it and run a current, the magnetic field causes those two wires to attract, or if they're running in opposite directions, they repel, right? So that is probably, if you're going to explain the magnetic field, that may be the simplest case that you might be able to explain. Because I don't think you want to explain, how the magnetic field comes out of the permanent magnet. Here's another mystery: is that we know that magnetic fields can be created by current loops. I mean, that's a solenoid. We can clearly do that, and it produces fields which are, as near as we can tell, identical to the ones that are coming out of the permanent magnet. But yet in the permanent magnet, we clearly don't see a wire in loop where you're forcing an electron to go through it. And even if there were a such loop, then unless it was a superconductor, that current should immediately drop off, and our permanent magnet should immediately become non-magnetic as the current runs out. But we don't see that. The permanent magnet is a mystery in that it's a current loop that doesn't stop. So therefore, to my thinking, that does make it actually a superconductor. So that was sort of one of the things that I'm thinking, is that since the permanent magnet does the same thing as the current loop, then the permanent magnet must have a current loop. And since it doesn't decay, it must be a room temperature superconductor. Is kind of what I'm thinking. But it's a superconductor in very, very tiny loops, right? Very, very tiny loops. Because if you look at a magnet, what you'll see is that there's these regions of magnetizations on the grain, and each little grain can be pointed in a different direction. But in a magnet, all of those grains are pointed in the same direction. So to me, those little grains are setting the boundaries for where these current loops can run. And but inside is a superconductor. So I'm thinking that that's a room temperature super. Somehow ferromagnetic materials, and that's the other mystery about magnetics, is that out of all the elements on the periodic table, only 3 can be considered naturally ferromagnetic, meaning that they can be made into magnets. And that's like iron, nickel, and the cobalt. And those elements are all just right next to each other. So it would seem to be that the only requirement is that it be of like this mass or this size, right? I don't know that there's anything particular about, say, the electron shell structure of these elements that makes them unique, because you can find exactly the same electron structure, up and down the rows in the periodic tables, right? If it had to do something, well, this iron atom has a free electron here or there, then you'd think all the periodic, all the magnetic elements would show up on, say, one column of periodic element. But it's not that. It's these 3 elements right next to each other. So that's telling me that it's actually size. That whatever the radius of this thing is, that is what is controlling whether it has the ferromagnetic property. Now, the other weird thing is that you can make supermagnet, like these neodymium magnets, are made out of basically non-magnetic materials. These are. So how can you take a bunch of non-magnetic materials, mix them together, and you come together, and it makes it into a supermagnet, right? So once again, I'm thinking that it's not the actual materials that make up the permanent magnet that matter. It's a matter of some atomic arrangement that allows it to create these superconducting loops inside. Right? So I'd be kind of curious whether you guys, what do you think of that hypothesis, that ordinary magnets, kitchen magnets, are actually some kind of superconductor? And that if we could figure out how that works, instead of just having the superconducting loop in a tiny little grain, if we could break those grains down such that they're really, really big, like the length of a wire, then that would be a way to create a superconducting wire, right? If we can get the superconductivity to still work over a large distance over there. So that would be the way forward to superconductivity. What do you think, James?
Well, it's interesting. I think you are clairvoyant, because I was just thinking that I wanted to comment that your postulation of superconducting loops sounds awfully like the electron and proton quanta cycles that I've described, where quanta will rotate within these cycles. And by the way, all particle motion is based upon quanta leaving one cycle and entering another. And that's all. I mean, that's just what I was thinking at that moment of time. And I think you are, in part, clairvoyant.
Yeah, that maybe a little reminiscent. Although that doesn't explain why is it that only iron and nickel and cobalt possess this particular thing. That's the problem, is that whatever theory of magnetism you come up with, you have to be able to account for the fact that it doesn't happen for copper and aluminum and all these other metals. Although
Agreed.
they would seem to be structurally similar, because that's one possible theory, that electromagnetism is caused by the electrons. I mean, the electrons themselves orbiting in the atoms is the current loop that causes the magnetism. But unfortunately, all the other elements do the same thing, right? So you would predict that all these other elements would be magnetic based on the same electron orbiting around the same spot in the atom. And I think they have actually done experiments to determine, if the hypothesis that the magnetic field is being caused by the atomic electrons is false. That they did some experiment to explicitly check that, and that turns out to be wrong. It's not the electron orbiting around a particular atom creating a current loop. So, like I said,
one theory might be that the electron shells of the three metals, which are great for making magnets that you listed, their electron shells may be appropriate or consistent with forming a polarized structure on a larger scale in what we call the crystalline lattice of a metal in the solid state. Okay, so like for example, if related to that is in my experiment where I just put in a bunch of magnetic monopoles, which are the L-type quanta, all in one direction, let's say up or down in the simulated space, I find that electrons and proton bits in those two different cycles both move in the same direction, but the electron quanta in electron spots move a little bit further. In other words, the addition of a magnetic pulse in the simulator, which is equivalent to adding quanta of the L-type in just one direction, let's say up or down, appears to be polarizing the material.
Well, I think that's interesting. You mentioned that we think that this effect, goes beyond the atom, that it's actually to the lattice, the crystalline lattice. And I think that's very important, because I think that these electron loops, if they form, are a property of the crystal structure, not the atomic structure.
Yeah, like the solid state people look at these metals, and again, I'm definitely not an expert in this area, although I've read a thick book on solid state physics, but I'm still not an expert. But my impression is that they're telling us that in the solid form, the metals form a crystalline lattice, and it could be that the electron shells of the three metal types that you mentioned as being very susceptible to storing a magnetic gradient. Um, their electron shells may be particularly suitable for when the crystal lattice is formed, uh, that they would maintain their directionality. And so a lot of the talk in several weeks past about magnetism and electric polarization that Franklin and others have mentioned, I think, uh, has some substance to it, as far as I can see.
Well, I'm still thinking further because you're still thinking that there's an alignment of individual shells. And I'm thinking that doesn't have anything to do with the individual shells. Has something to do with a certain dimension that these atoms possess, such that when they form the solid state crystal lattice, that the electrons have a free path, a free superconducting path to move into this crystal lattice, which may consist of millions of individual atoms. So the smallest.
Oh, okay. Well, that's an entirely different idea, which could have merit also.
That's what I'm thinking, is that in order to create, I mean, it would be an interesting experiment to see what is the smallest bit of matter that can have that can represent a permanent magnet, right? So I would say that at some limit, you would get to a point where it's just too small to be a magnet, that it doesn't have the right properties for the electrons to form a current loop. And then that would kind of give you a specific dimension. I mean, if you found such a thing, right? There may be a specific dimension which is favorable to the formation of these current loops. And that's important because then that would give you a standard by which you could go and then check to see whether, well, can I make some other material? Now, I mentioned these superconducting magnets, are basically consist of these rare earth metals, which are basically non-ferromagnetic. But you put them together, they somehow form this crystal structure. And if you knew what the optimal distance was, then you could say, aha, instead of using these elements to make the magnet, if I use these other elements, maybe cheaper elements, that maybe I can make an even stronger magnet, right? And that would be a tremendous boon to, because all of our high-tech stuff, from our headphones and hard drives and things like, use these super strong magnets. And the stronger you can make your magnet, the lot more things you can do with them. So to those guys, but basically, we're going rule of thumb. It's randomly guessing. It's just alchemists just putting together every possible element. This is what they do for superconductors too. It's like they don't have any real good idea of what the working theory is. So just like alchemists of past, they just take everything they've got on the shelf, stick it together, and try it, right? And do that with every possible element.
I suspect that materials engineers and solid state physicists, condensed matter physicists, are probably in the not too distant future will be able to predict or come up with some theme. Again, the role of intuition in advancing physics, which would predict a certain combination of materials that hadn't been tried yet, and lo and behold, their prediction is correct that it does have this this property. So I think we're close to that.
Well, some other hints that we see in permanent magnets are, you've seen like the common ceramic magnet that you get when you go shopping and you stick that on your refrigerator. Now, the interesting thing about that is that the best magnets are non-conductors, right? This is why iron is not a very good magnet, because it's a strong conductor. It seems that the best way to make a magnet is to make it with non-conducting materials. But now, I just said that what a permanent magnet must be is a superconducting loop in there. So how can you build superconducting loop out of things that don't conduct electricity? And I think the trick here is that in order to have a good superconducting loop, you want to make sure that the electron doesn't leak outside of the loop, right? Because if the electron can just go loop, 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 and then just go off to someplace else, then it's no longer a loop. So one of the main principles of making a strong magnet is that whatever this loop is in has to be insulated, non-conducting. So this is the reason why, I think like all these other superconducting magnets are also, non-conducting. I mean, they put a nickel coating on the outside so that you could see that they're conducting. But if you got on the inside, and I don't suggest you do that because apparently these materials are super nasty, and that's why they coat them in the shiny outside coating that you see. That they're forming a good magnet because their electrons are stuck in the crystal grains that are form the superconducting loops, right? So this is another thing you see. Another hint, which is the strongest magnets are the magnets which do not conduct electricity, right? Which have highly restricted electron movement. And the other hint is that I give to you is actually how they make these magnets, which is they form the alloy of the material, they mix together all the stuff. But then what they do is they grind it down into a powder. They grind it down to a powder, then they sinter it, which means that, you don't melt it or anything like that. You literally compact this powder into like a block. Then they put that block into a magnetic field, which allows the individual grains to align optimally to the magnetic field. And then only at that point, then they put a really high pressure and temperature on the magnet to sinter it in place and make it a hard thing. And then you've got the really good magnet. You cannot make a really good magnet by just pouring it into a mold and then charging it with a magnetic field. That's not the most effective way to do it. First, you have to make it into a powder, align all of the powder so all the tiny little magnets that make up the powders are all completely aligned, and then charge it with a magnetic field, and then you get a really good magnet. Once again, that's all kind of consistent.
Okay, my impression is when you say all the little tiny magnets, I would prefer, well, is it correct for me to think that really we're talking about objects, atoms or whatever, or compounds in this ceramic mixture, which have an electric dipole moment, and when you expose that in the final phase of manufacturing your ceramic magnet to a homogeneous magnetic field, those particles then align with their electric dipole moments. So and then they're fixed in place when it's finally solidified, and then you have a magnet. So that here we're looking at, if my impression of this is correct, that actually the alignment of a whole lot of particles, let's call it the alignment of their electric dipole moments in a solidified object, is what gives you a magnet. Now, where am I wrong there?
No, I think that's basically right. But the each of those little grains, after they take the solid bar and they turn it into dust, each one of those little dust particles, which you could see with a magnifying glass, which would still consist of, I don't know, probably millions of atoms, has a magnetic moment, and it acts like a small magnet.
Okay, but when you say has a magnetic moment and a small magnet, I'm focusing on the fact that these little particles have an electric dipole moment. In other words, that there's an asymmetry in the charge distribution within those little particles, and that exposing them to a homogeneous magnetic field in the final stage of manufacture aligns these electric dipole moments, and then they get all aligned, and you have basically a magnet.
Well,
So
I would say that we definitely have electric dipoles, but I would say in the materials we're talking about here, which are like metals, those the I don't think that really has an impact, because the electric field and the magnetic field are still two different things. It's not like this particle's got a positive end and it's got a negative end. If you put that particle in the magnetic field, it's still basically not going to do anything, or maybe it does, but that's not the major influence that you would have. In order to have a major influence with your electric dipole, you'd have to put it between a positive and negative field, and then you would see it strongly twist and torque due to that. But magnetic field is different, from the electric charge, and that's one of the other mysteries that we have, which is that the electric field seems to be, very far-ranging, 1/r² kind of force, but the magnetic field seems to be more short range. It's like a 1/r³ kind of force. It can't get very far, from the magnet compared to, I don't know, say, electrostatic field, which is much stronger. Now, I kind of attributed that because, we had talked about polarization, right? And I think that the magnetic field has to affect the outside regions of space, I think, in a polarization kind of way. Which means that there's something in that space that is pointing in a particular direction, right? And when you're talking about non-magnetized space, those things are pointed every which direction. But in magnetized space, all those things are pointed in the same direction. So there's something which is getting polarized out there in space. But so it looks like we've come to about the end of our time here. So let me just try and summarize. So today we've had Dennis and James here today. Actually, not that many people participating in the live green room here today. But so James started out by having an update on his fine structure constant alpha. So he made some adjustments on whether you're looking at the simulation at the beginning of the time tick and the end of the time tick. Made some adjustments there, hopefully making the predictions of alpha more accurate. And we had discussed, what are the predictions of bit mechanics, and that he's predicting that alpha really isn't a constant. That if you were to perform these same experiments in, say, plasma environments, you should see a difference in alpha. Although I've not, just looking at the internet here right now, not found any evidence that anyone has said that alpha at any given time is experimentally different. That's what scientists normally do. They go and they have, if they declare it constant, it's like hundreds of people measure this, and they should all come up with exactly the same value. So any evidence that they do not would be supportive of James's hypothesis. However, the flip side of that is if you've seen that they've done all of these experiments and you verified that they've actually done it in what you feel are sufficiently different situations, like you do find a situation where they did something in a highly energetic environment, some guy you saw clearly did something in a low energetic environment, and those people didn't come up with any differences, then you would have to say that would be not in support of James's theory. But I think that's good. It's good that your theory can be disproven, because I think if you've got a theory that just simply can't be disproven, it can accept anything, then that's pretty worthless. So I think that's always a good thing to look for in anybody's dissident theory, Can it be disproved? Does it predict things that haven't been measured? I think is a key there. And then we also discussed, what is the nature of the intrinsic electron moment, which James says he can calculate from the 3 fundamental constants of mass, length, and time. Now, I didn't give him a chance to say this, but I'm going to just say my piece on the intrinsic electron moment, and that I don't believe that an electron has a magnetic moment. Like, it's not a magnet, right? Because the electron field actually requires a conglomerate of aligned particles. Like I said, the magnetic field creates this polarization. The polarization can only happen in a large group of particles. The individual particles that make up those things, like the individual electron itself, cannot possess any kind of magnetic field. And I would argue that what they're measuring is when you move an electron, then that immediately creates the magnetic field that you're measuring, right? I would assert that every single experiment measuring magnetic moment involved a moving electron, and that moving electron immediately creates the magnetic field that you are measuring. But if you took a totally stationary electron, I would say it is impossible to measure any magnetic influence coming out of that thing. That would just be my prediction. And if that's not true, if someone has done a magnetic detection on a completely stationary electron, then that would just blow away my theory, showing that my theory predicts things that are wrong, right? So my theory is, like James's theory, can be proven wrong because it makes very specific predictions. My very specific prediction is that the electron magnetic moment doesn't actually exist on a stationary electron. That would be my prediction. And but yeah, that's my piece on electron magnetic moment. And then we start getting a little bit into discussion about what's going on, how magnetic fields are long distances. So James is trying to explain that anything that happens over here does always have a propagating effect somewhere out in the rest of his model. That just happens, right? So and then we start getting into discussion about what is a permanent magnet, right? And I have my hypothesis that a permanent magnet is actually a superconducting current loop in the individual crystalline grains of the magnetic material is kind of my hypothesis, and that knowing that we could perhaps make better magnets, right? But that will do it for this week's episode of the John Chappell Natural Philosophy Society. So hope to see you guys all back here next week then sometime. All right, so bye-bye.